Welcome to The Explainer. Today, we're diving into a topic that is, well, seriously mind-bending. We're talking about quantum computing. I want you to forget everything you think you know about how computers work, because we're about to step into a world that plays by a completely different and, frankly, much weirder set of rules. So where do we start? Let's kick things off with this absolute bombshell of a claim from Google back in 2019. They said their quantum processor did something in just a few minutes that would take the world's best supercomputer 10,000 years. This was the moment they claimed quantum supremacy. And just like that, a new kind of arms race was on. But the celebration didn't last very long. IBM, the company that actually owned that supercomputer, fired back almost immediately. They basically said, hold on a second, your math is wrong. They argued that their machine could actually do it in about 2.5 days, not 10,000 years. And this kicked off this huge, messy debate. What does supremacy even mean in this context? Had we really crossed that line? To really get what all the fuss is about, we've got to take a quick step back and look at the computers we use every single day. We need to talk about the foundation of everything digital, the humble, reliable BIC. You know, every photo on your phone, every song you stream, all of it, it's all just built out of these tiny little things. Think of them as the Lego bricks of our digital world. They're the absolute smallest piece of the puzzle. And here's the crucial thing you have to remember about a bit. It's definitive. It's like a light switch. It's either on, a 1, or it's off, a 0. It can't be anything in between. It's never both. This simple black and white logic is what has powered our entire digital revolution. And we use a ridiculous number of them. A single gigabyte of data, that's 8.5 billion of these little on or off switches. They can handle incredible amounts of information, for sure, but they do it one step at a time, one calculation after another. Okay, now for the fun part. Let's see how quantum computers take that fundamental rule and just completely shatter it. We're now leaving the world of the bit and entering the wild, strange world of the qubit. So here's the first piece of quantum magic. It's called superposition. Unlike that simple on or off light switch, a qubit can be a 0 and a 1 at the exact same time. It's not one or the other. It's a blend of both. It's kind of like a dimmer switch, holding a whole spectrum of possibilities all at once. You know, a really great way to get your head around this is to picture a spinning coin. While it's up in the air, spinning, is it heads or tails? Well, it's neither. It's in a state of pure potential, a mix of both outcomes. That's a qubit in superposition. It's only when it lands, when we measure it, that it has to choose. And here is where things get really crazy. Because each qubit can hold multiple values, when you add more qubits, the power doesn't just add up, it multiplies. It grows exponentially. 2 qubits can explore 4 states at once. 3 qubits can explore 8. 4 can explore 16. You can see how this power just explodes. So let's put that into perspective. That Google chip we talked about, it had 53 qubits. That means it could hold and process 2 to the power of 53 states simultaneously. That is a number so big, it's hard to even imagine. It's over a quadrillion calculations happening in a single step. Insane. The next layer of quantum weirdness is something called entanglement. You can link 2 qubits so their fates are perfectly intertwined. If you check on one and find it's a 0, you instantly know its entangled partner is a 1. And this is true even if they're on opposite sides of the universe. It's so strange that Albert Einstein himself called it spooky action at a distance. And finally, there's interference. So if qubits in superposition are like dancers exploring every possible move at once, you can think of interference as the music that guides them. You can carefully control them to make the paths leading to the wrong answers cancel each other out, while the path to the right answer gets louder and louder. So we've got this incredible, almost unbelievable power from superposition, entanglement, and interference. But, and it's a big but, actually using that power is one of the biggest engineering challenges humanity has ever faced. Let's use an analogy to see why. Imagine you're trying to solve a really complicated maze. A classical computer would have to do it by brute force. It tries one path, hits a dead end, goes all the way back, and tries the next one by one. For a really hard problem, this could take, well, thousands of years. A quantum computer, on the other hand, thanks to superposition, gets to explore every single possible path through that maze, all at the same time. It doesn't find the answer by trial and error.
It just sort of sees all the possibilities at once and zeroes in on the right one.
But, and this is the massive catch, that beautiful, powerful quantum state is also incredibly fragile. I mean, unbelievably delicate. The slightest little disturbance from the outside world can make the whole thing just collapse. This huge problem is called decoherence. It's what happens when the outside world essentially looks at the qubits, forcing our spinning coin to land before it's supposed to. A tiny vibration, a stray bit of heat, even a single photon bumping into it can destroy the superposition and completely wreck the calculation. And this is why quantum computers look like those crazy, elaborate chandeliers you see in pictures. To stop decoherence, you have to create one of the most extreme environments on Earth. We're talking colder than deep space, perfectly shielded from any vibration or magnetic field, all while running incredibly complex error correction just to keep things stable. So with all these insane challenges, what does the quantum future actually look like? Are we all going to be carrying around quantum laptops in a few years? Well, the short answer is a definite no. Don't expect to be checking your email on a quantum computer anytime soon. These aren't general-purpose machines. Think of them as highly specialized tools, custom-built to solve a very specific class of problems, the kind of problems that are literally impossible for even our best supercomputers to crack. So what kind of problems are we talking about? We're talking about designing new life-saving drugs molecule by molecule, creating revolutionary new materials with properties we can't even dream of today, building far, far more accurate models of our planet's changing climate. For the first time, we'll be able to use a quantum system to perfectly simulate other quantum systems. But really, the truth is, we are at the very, very beginning of this road. It's a lot like being back in the 1950s, looking at those first computers that took up entire rooms. No one back then could have possibly imagined that technology would lead to the internet, or smartphones, or social media. The most amazing applications are probably things we haven't even thought of yet. And that really leaves us with this final, massive question. For the first time in history, we are building machines that operate on the fundamental quantum rules of reality itself. We are unlocking a type of power that is completely new. So the real question isn't just how they work, but what will we as a species choose to do with it? What grand challenges will we decide to solve?